All right, if everybody could pass up that in-class exercise, pass it over to this corner over here, Marissa. So what did we do last class? We talked about Kruskal's algorithm for hope. Before I start, I'm taking some students out to lunch today. So the first 10 people that want to join for lunch today, it's Chinese food on the corner, my treat. First 10 to group outside after class. And what did we do last class? We talked about basically the minimum spanning tree problem. We considered the first degree solution, which was Kruskal's algorithm, and we generalized it to a general MST strategy. We looked at that strategy and we considered a specific implementation, one that's easier to implement than Kruskal's might be, and that was Prim's algorithm. Today we're going to continue with the discussion and analysis of Prim's algorithm, and then we're going to make another observation, which is that a very simple tweak to the algorithm that we have right now actually will solve another problem, a shortest path problem, and it leads to Dijkstra's algorithm. So all of these algorithms are very connected. Dijkstra's is another greedy algorithm. Instead of solving the minimum spanning tree, it solves the single source shortest path problem in graphs that have a special structure. In particular, graphs that have positive edge weights. That's the plan today. Okay, minimum spanning tree. Now remember that the minimum spanning trees, we're looking for a set of edges, a tree, that connects all of the vertices in the graph. So every pair in the graph, there's a path in this tree between those two vertices. And it has the least cost according to this function. By cost of the tree, we're just taking the sum of the weights of the edges in that tree, and we're looking for the least cost, the minimum cost spanning tree. We talked about a few definitions to talk about this problem intelligently. The first one was a notion of a cut. A cut is just a partition of the nodes. Any partition will work. What happens when you cross the cut, or you cross this cut? That means that for a given partition, for a given cut, S and V minus S, to cross that cut means it's an edge like DG, where one part is in, one vertex of the edge is in S, and the other is in V minus S. That's what it means to cross the cut. So in this case, these four edges would cross the cut. Respect. An edge respects a cut if it doesn't cross the cut. And that leads us to the main insight to these class of problems, to the minimum spanning tree class of problems, which is that if we have some set of edges that is already part of a minimum spanning tree for some graph, and we consider any cut that respects A, i.e., in other words, A, none of the edges in A will cross that cut, then the minimum weight edge that crosses this cut will be part of our solution. Handful to say, but it's an intuitive property, and it's actually the property behind dozens of efficient algorithms for this problem. The key insight. This was an example of it. Here was we have part of an MST so far, these two edges, and this could now be S, and that could be V minus S. And it turns out that this edge right here would be part of the minimum spanning tree. Okay, so at the end of last class, we had this general minimum spanning tree, which we have proven that this algorithm is correct.
The cut theorem says if we start with some subset of a minimum spanning tree, which in particular the empty set is a subset, and then we pick some cut that respects A, and we find the min-weight edge that crosses this cut, then we can add that to our solution, and we still have a partial solution to the minimum spanning tree. Since we know that the size of the tree has to be v minus n, this general strategy will do it. We already know that it's correct. All that remains is to find an efficient implementation of it. Kreskel's did this by finding the smallest edge which doesn't create a cycle, but that task of actually determining whether an edge, adding it, would create a cycle requires a fancy data structure to do that. Instead, we're going to use a simpler data structure by taking a simpler version of 3, 4, and 5. In particular, Prim's insight was as follows. What we're going to do is keep A as a tree already. We're going to maintain A as a tree. And then in order to pick a cut that respects this tree, all we have to do is set S to A. And we know that that such a cut respects A because, in particular, it contains all of A in one side of it. And then the problem becomes finding the minimum weight edge which crosses this cut. So if you have some partial tree like this, if you have some tree so far, all you got to do is figure out which is the lightest edge that leaves that tree. So you have some partial tree already. You just got to figure out the lightest edge that is connected to your tree, that emanates outside of your tree. And that's the edge you want to add to this minimum spanning tree. And now when you come across this problem, right now, notice that before we had to determine whether an edge creates a cycle. And now we've reduced the problem to all we got to do is find the lightest edge which is connected to me so far. This is a nicer property to actually compute. We already know data structures from 2150 for dealing with find the smallest element of a set. In particular, we could use a min heap or priority queue. Right, so that was the data structure that, well, before I actually get to the data structure, let me illustrate how the algorithm works. So Prim's algorithm starts with some arbitrary node, D. And now D is, of course, a tree. It's an empty tree. It has no edges. And the idea of the algorithm is to pick the lightest edge which is emanating from this tree. Well, so far, there are only 4 edges that emanate from D. They have 8, 5, and 7. And the lightest one, therefore, is 5. And so now, in the second step of our algorithm, this is the tree that we now have. And of course, we use the cut theorem again. We set S to be this tree. And now we find the lightest edge which emanates from this tree. And now we had 8, 7, 8. And we have 3 new edges, 6, 9, and 11. Okay? And it turns out that 6 is going to be the lightest one. So we go ahead and augment that. And now our tree is like this. Okay? Remember, these are the lightest edges which are now emanating from our tree. And in this case, it's going to be 1. And once we add this node, these 3 edges become part of our tree. And so one of these edges 3 that we can pick. We can pick an arbitrary one. By adding that, we don't add any edges to our tree anymore. Yeah, so the point is that once we add E to our tree, this edge 3 no longer emanates from our tree. So we don't consider it anymore. And then we continue as such, and you know the rest of the tree. Okay, so we're going to go over this example in more detail with the actual data structure, but that's the basic idea. Right, and so now the implementation idea is going to be So we're going to, again, set the set S right here. The cut that we want is going to, S is going to be A. We're going to, the key idea is we're going to use a priority queue to maintain the set of edges that emanate from A, and that will let us easily pick the lightest edge in log n time. And then by the cut theorem that this lightest edge will be part of our solution, and we continue. Right? So in last class, I talked about the operations of a priority queue. All of these insert, make the queue, extract, and decrease key. And we knew that basically all of these operations run in basically log n time. I'm not going to go over that part again, and I think most of you are familiar with that data structure. So let's get to it. Let's get to the algorithm that we actually have in mind. So what we're going to do is for all of the nodes in V, we are going to set their key to infinity, and we're going to set their back pointer to nil. This back pointer is how we actually keep track of the tree. Just like backtracking in dynamic programming, this back pointer will help us at the end recover the actual tree. And now we're going to pick some random node R, and we're going to set its key to 0. And now we're going to make a queue with all of these nodes and their keys. Okay, and now here's the crux of the inner loop of this. While the queue is not empty, we're going to pick the minimum node in this queue. Now remember, we're maintaining a tree. Every time we add some node to this tree, we need to add all of the edges. Because we need to keep track of all the edges that emanate from this tree, when we add a new node to this tree, we look at all of the edges that this new node has, and we want to add them to our data structure. Okay, so that is basically the algorithm. For each of the neighbors, we've picked the way that this tree is going to grow. We've picked the node that has the smallest weight so far, and now we want to add all of the edges that this new node will add to our tree. And so for every neighbor, if this neighbor is in the queue still, i.e. it hasn't been already taken into our solution, and its weight is currently bigger than the weight from U to V, we're going to update the weight of that node by calling decrease key, and we're going to update this pointer problem. A good way to understand this is to actually go through, and this is the role of the first handout. Everybody have one? What better way to understand this algorithm than to step through it? Okay, and so notice in these first three steps, what I've done is added, so I've added all of the nodes to the queue, and this designated node D has value 0. And so now let's start stepping through lines 5 through 10. What happens? We extract the minimum, which in this case is 0, since all of the other nodes have weight infinity. Now for each of the neighbors, if these nodes are, so the neighbors of this node are B, E, H, and G, they are still in the queue, and their weights are currently infinity. So in that case, what we're going to do is decrease key. We're going to run a decrease key operation. So we'll change this to 8, 8, 5, and 7. And then we'll also set this back pointer. So in this case, what I'm going to do is draw this red arrow to say, what this designates is that so far I get to G by going there. I get to G from D. That's what this back pointer says. And eventually, at the end of this algorithm, all the arrows that are left will be part of the minimum spanning tree. So this is the state of the graph after the first iteration. So now in the second iteration of the loop, which node are we going to pick? This node H, right? Just as I explained intuitively, but I want you to make sure you understand how it does in the code. So now at line 6 in the second iteration, we're going to pick line H, and we're going to inspect all of its neighbors and update all of their links. So in this case, this will be 11. In this case, G is already 8, and so its weight is currently, so 9 is not less than 8, and so no update on this node occurs, but this node becomes a 6. Okay, and additionally, we set these pointers for the nodes that we updated. If we updated, since we updated I and F, we set these red pointers as such. Now, how about we spend 5 minutes with your neighbors walking through the rest of this algorithm? The point I want you to make is to make sure you understand essentially how it works. As soon as you get a good sense, look up and raise your hand, and then we'll talk about how to analyze the running time of this algorithm. So go for it.
These red arrows keep track of all of the red eggs that are into this. Well, yeah, the blue ones in the right ones on both sides. I'm using the blue to represent the CA, and I'm using red to represent the ingredients. At the end of the argument, each node will have ID, which is its parent in the minimum spanning tree. Okay, does everybody have enough time?
Everybody have a good understanding now how this works? Yeah, question? Do you ever remove arrows? You can change arrows. So, for example, take a look at this node right here. Pi v, so pi e right now is currently D. The parent of node E in the MST right now is D. But notice what happens in two steps. So in this first step, right, when we consider, when we begin to extract 6 right here, we consider its neighbors, 3 and 1 right here. So when we do this check right here, we're going to say, because E is a neighbor of F, currently the key for E is 7, but the weight from F to E is 3. And so we're going to do a decrease key operation. We're going to change this to a 3, and we're going to replace this edge right here with this edge right here. So edges do get replaced, if that's what you meant. And in the end, this pi v stands for the parent of the node V in the MST. So once you run through this loop, all of the red arrows that will be left, all of the pi v links, will actually be the solution to your minimum spanning tree. Question? Every node has its own pi v. We first set them to nil, and at the end of this loop, you should convince yourself that everything connected will have a pi v set to it. The first time it's touched by the first time it actually gets in this part of the loop, it'll actually be, pi v will be set. Question?
So in last 6, when you have extracted, what is it?
So, very good question. I didn't specify that clearly, but remember in a priority queue, this insert operation, or this insert operation is going to have a node and a key. So each of the nodes basically has some key, and when we start this, we initialize that key with infinity. And as we update it with this weight of this edge. So the extract min is going to be with respect to the key, kv, and the kv is what we're updating with the different weights. Some of you might have encountered this Prim algorithm, this minimum spanning tree. I think in 2150, maybe you program it, and you consider it from the data structure perspective. And so now we're considering it from the algorithmic perspective, why it works, right? And the best way to understand something is to see it from various angles, different angles, implementation, from data structure point of view, and now correctness and algorithmic perspective. This is a combinatorial problem on a graph, and we're solving it with this neat, greedy algorithm. Right, so as we walk through this, various nodes get updated, and so forth. If you understand this algorithm, you should now be able to help me figure out what the runtime of this algorithm is. The easy part is all of this stuff. Step 1 through 4 is going to take theta v time, because we do some operation for every vertex in the graph. And inserting all the nodes can be done with this special way with the priority queue that takes order v time. So the hard part is going to be analyzing these lines, 5 through 10. Now the first question, how many times will this extract min operation be called? V times. And each operation takes how much time? Log v. So this line is going to contribute v times log v time, because it's repeated v times, Okay, so line 6, check mark. We've analyzed that part. What about the rest of this? This is kind of a tricky loop right here, 7 through 10. And this is basically constant time work here. It's not very important to do this check. The only real other operation right here is this decreased key operation, which we know that one instance takes, again, log v steps. Now the trick, though, the idea is that as we loop, see this is a nested for loop, and so it's kind of hard to know. In the worst case, we can overestimate and say that, you know, at most there are v neighbors for each node, but that's going to give us an incorrect running time. It's going to give us like a v squared runtime. Well, we're actually going to do something slightly more subtle, and we're going to say that throughout the execution of this algorithm, each edge is going to be inspected at most twice, right? So this inner part of this loop, it runs at most So everybody see that? Lines 8 through 10. Overall, through the entire execution of the algorithm, those lines are going to be executed at most 2e times, or order e times. For every edge in the graph. So that means that this line right here gets executed at most how many times? This line contributes how much time? Exactly, e times log v. So overall, the runtime is order we basically say it's e log v because there are typically more edges in the graph than there are vertices in a connected graph. Does everybody understand how we did that type of question? Shouldn't there be a factor of v where? For each vertex here, so once we extract u, we're going to loop for all of u's neighbors. And then we're going to loop for some other vertex's neighbors and some other vertex's neighbors. So I'm not analyzing this in a nested loop. That would be an overcounting. What I'm saying is, during the first time, we know that this while loop is going to execute v times. Do you have a response? Or? Yeah, this do is just a typesetting. The LaTeX package, which typesets algorithms, expresses it this way. It's not like the C. Basically, the while this condition is true, do this, instead of a nested loop. So I don't know if that addresses your question. The point is, this loop, this outer loop, is going to run over all v times. But on the first time, it's only going to do, let's say, the neighbors of first node. The second time, it's going to do the neighbors of the other guy's node. Overall of its iterations, at most it's going to run e times. Does that make sense to everybody? Do you want to talk about it with your neighbor? It's a nice critical point. A minute with your neighbor. Explain, convince them why this accounting is correct.
First 10.
So was that first 10?
I don't know. Someone have to probably see it first.
Are we good?
Okay. Everybody comfortable with this?
I've walked around a few times. Many groups have come to the same idea that for every edge in this graph, when one party of the edge is selected as extract min, that time could possibly create a decreased key operation. And when the other party is chosen as extract min, that could possibly be a decreased key operation. So at most, there could be order E such decreased key operations through this global algorithm. And that's how we get to this E log V runtime for this. This is a start. Prim did this in 1958. People have been working on it for the last 70 years. And here is some here are some updates. So a big jump in the 80s. So a new type of data structure. So instead of priority queues, which have log n, log n, log n, this gentleman Tarjan at Princeton, he came up with this cool idea, which is to say, look, insert will be fine log n, extract min could be log n. I really want to find a clever way to do decreased key operations. And so he came up with a new theory. It's this like, sort of not a new theory, but this amortized analysis. We talk about this in the graduate version of this course, what a Fibonacci heap is and how the analysis works. But the basic idea is that amortized over all of the E operations that you're going to do, he figured out a way to make decreased key run in constant time. Very clever thing. And if you look at that, right, if you go back, if this operation is order 1 amortized, then the running time is going to be order E, right? That's where the E log V came from, E plus V log V. And so immediately you have something that's much faster than the previous thing. This Fibonacci heap, it's kind of a cool thing. It was actually implemented in some Microsoft file system data structure in the 80s as well, after a few years after it was, came out. So it's kind of it's both theoretically interesting, and it was implemented in practice for a very mainstream operating system at some point. Now, the work hasn't stopped there. This is such an interesting, clear, simple combinatorial problem. Lots of people have made, so this was Fredman and Tarjan, not just Tarjan. But everybody has sort of successively optimized this. This very cool result by Seth Petty and Vijaya Ramachandran, University of Texas, they have an algorithm. Get this. They can show that their algorithm is optimal up to some constant. It's the best you could possibly do. They can prove that it's optimal, but they don't know what the running time is. Pretty cool, huh? It's an amazing result. Whatever their algorithm does is within a constant of the best you can do, but they don't know what the algorithm actually does. Question? The number of edges in the minimum spanning tree is always v minus 1, but the input graph, you don't know which ones are part of the MST, so the input is E. In the graduate version of this class, we also spend 2 lectures talking about this amazing result. This is one of the reasons David Carter, who is at MIT, won the best dissertation award. This paper right here. They're able to. It's a randomized algorithm, so it uses random coins, and it solves this problem in order E time. Amazing. And of course, there's special cases of this problem. For example, when you do like when the graph is Euclidean, the distances are Euclidean. They satisfy the triangle inequality. Then you can do this. You can do it in V log V, which is even better than E in many cases. Question.
Yeah, they described an algorithm, and there are a few very interesting results like this, but they described an algorithm, and they described each step, and of course they can argue something like, they can argue
Some very, just like we could on our algorithm, if we were lazy,
we could say, yeah, it runs in EV log V. Could have said that, right? But we did a slightly more finessed analysis and showed that it was actually E log V. And similarly, they could make some argument that it runs, they could take any of those running times above, right? Because they could say our algorithm runs in this much time. But they're able to do it slightly further. They're able to say, whatever the best time is for this particular algorithm, we achieve it. And I can't recall the exact argument that they use for this, but it's a very complicated algorithm. It's broken into several parts. And I don't even know off the top of my head what the approach is.
we can talk about it though, and you can easily Google this paper and read the abstract. That would be a very mean homework problem. But thank you for the suggestion.
Put a star by
it. I want to talk about one application of this minimum spanning tree. If you use Kruskal's algorithm, you can actually do this K-clustering. So suppose you have a set of points like this and you'd like to cluster them into sort of K-means clusters. What you can actually do is start taking Kruskal's algorithm, find the smallest link and make that a cluster, find the next smallest pair and make that a cluster, and you keep on adding, essentially, you keep on adding nodes, and if you want to, and you can continue. For example, if you want to figure out, where to put a Starbucks, for example, and these are where people live, and you say, I have enough money to put 4 Starbucks in the place. Where should I put them? Where should I put them to maximize the, distance to the people and so forth? You can cluster like this, running Kruskal's algorithm for a certain number of steps, and then you can put your Starbucks in the middle of each of these clusters. This diagram is, the PDF is a little bit warped, but that's the idea. So yes, you can do it. You can use this minimum spanning tree algorithm for a form of clustering. It gets even better. For the price of one, you get not only one algorithm, but you get another solution concept. Imagine you had the simple question of what is the shortest length. This was, for example, that city, town that we talked about, and you wanted to find the shortest path from A to E. You do this on your Google Maps or Apple Maps all the time when you're driving places. How do I get to point X, and what is the shortest way to get there? Perhaps including traffic, etc. This is a shortest path query, and it turns out that the same idea. So in this graph, it's very simple. You can imagine very complicated graphs where you want to see. In this case, you might even be asking the question: is there a path from here to here? Right. So if you model this as edges have weight 1, and you're trying to ask whether the shortest path is some finite number or infinity, right? This is a sort of connectivity question. You want to spend the rest of your class doing that? Okay. So we're going to define this new quantity, delta SV, and this is the length So delta SV, it's the length of the shortest path from S to V in G in this graph, in this weighted graph. And we're going to assume that all weights very good. So what I'd like to do is say that that same pattern that we use for minimum spanning tree, by making a slight adjustment to it, we can actually solve this shortest path problem. So in this case, instead of starting from D, I'm going to start from A, and I'm going to set its value to 0. And just like before, I'm going to extract the first node from this tree. So I'm going to, the smallest vertex, the extract min would return A in this step. And then what I'm going to do is update the neighbors of A. So I'm going to say here, in fact, are these pointers. And now I'm going to set this to 10 and this to 12. So far, it's just like our minimum spanning tree algorithm. And this is the state of the world after, one small point is that the arrows are going to point in the opposite direction in this case. So now the next step, I'm going to, again, extract the minimum from this queue. So this time 0 is out. I've indicated nodes that are out of the queue by making them gray. And so the only nodes in the queue are 10 and 12, and the rest are infinity. So the smallest one is going to be 10. But this time when I update, instead of using that previous update rule, what I'm going to do is make D here, instead of 8, I'm going to make it 18. Okay? And this one already had 12, so I'm not going to update it because updating it to 19 is not right. Okay? And similarly, I'm going to put an edge like this. So this is the picture of the queue after the third step. And now again, I take my smallest node in this graph, which is now 12, and I update its neighbors. So in this case, there's no point in updating this one or this one. They've already been extracted from the queue. But now this one, instead of infinity, I'm going to update it to what? 15, exactly. And I'm going to update this to 13. Okay, and so the graph will look like this after that step. Again, the next step, I'll do 13. And there's no point in updating this one because 16 is greater than 15, so there's no update. But in this case, I will update this to 19. Okay. And now the next node is going to be 15, but there's no consequence to that because 22 is greater than 18. Okay. And at this point, 18 is the smallest node, and so we'll update this one to 23. Oh, sorry, 26. Yeah. Now it becomes... Now here, at the end, there's one last phenomena that this is why I've got all the way to the end. I unfortunately picked this example here. 19. I don't update this one. I don't update this one, but I do update this one to 30. Okay, and I set this back pointer like this, so the graph is like this. But now finally, in the very last step of the algorithm, when I consider this 26, I update this node to 28, as such. And I change the back pointer from this one to that one. And notice these green edges. Everybody see the pattern. The minimum spanning tree versus what I'm doing here. I just changed what I was updating. Instead of updating with the weight of the edge, it was the weight of that edge plus my current. Okay.
what's left here are the distances of the shortest path from A to every node in the graph. In addition, the green arrows are actually the shortest path.
So for every vertex in this graph, the value dv, the key that I'm keeping at, instead of calling it kv now, I'm calling it dv, for distance v. It's going to be this value delta av, i.e. the length of the shortest path from A to V. And the green arrows are going to be the actual paths. But this algorithm is very similar to the one that we just talked about. Okay, if I were to write it, it's going to be the same init code. It's exactly the same except for this little condition right here. In particular, I think the next slide will have the comparison. So in Dijkstra's algorithm, we update if this is the condition, and in Prim's algorithm, we update if that's the condition. Okay? And the only thing that's different is the condition on what we update and the actual value that we update to. Otherwise, these two algorithms are the same. But they're solving very different problems. One is solving a spanning tree problem, connectivity, and the other one is solving a shortest path problem. So although the algorithms are similar in structure, there's a slightly different reason for why the shortest path algorithm works. Okay, and now let's go through that. Well, before we do that, first, everybody notice that this is going to be essentially the same running time as Dijkstra, as Prim, right? Because it's roughly the same operations. So then the only real question to answer is, why does this work? And in order to answer that question why it works, we have to do two things. So first, this is a one-page proof. We're going to go over that in these last few minutes. In order to use that proof, we're going to need these two properties. I'm just going to state the properties. You'll have to think about why they're true. The first property is that for every edge in the graph, delta SV, so the shortest path to V, has to be no more than the shortest path to U plus the distance from U to V. So in other words, the shortest, the quickest way to get to Paris, it can be no more than the quickest way to get to any city in the world and then getting from that city to Paris. So the quickest way to Paris for me is either IAD to CDG or JFK to CDG or ATL to CDG, one of those hubs to Paris, right? Same property right here, which we call the triangle inequality because if you think about it, the shortest way from here to there can be no more than the triangle, right? The shortest path from here can be no more than this triangle. Okay? The second property that we're going to need in this proof is that at every point in this algorithm, dv is greater than or equal to the shortest value. That's true at the beginning because we initialize dv to what? In this algorithm, what do we initialize dv to? I think so for the source, we set that to 0. For the rest of it, we set to infinity. Does that make sense? Okay, so it's too complicated to go over this proof. So here's what I want to do for the last few minutes of class. I want everybody to read over this proof. There are two parts of this proof that I want you to fill in, and that you will know that you understand it if you can fill it in. So in the middle of this case, there's a sentence. Suppose, for the sake of contradiction, that du is not the best answer, the best delta SU. Then there must be some path to u in this graph because ... I want you to answer that one. Okay. And the second part is going to be drawing a picture. And this picture is going to look something like this. That's what the picture is going to look like. You have to understand how it works. The basic structure of this proof is as follows. We're going to prove a property. That is, everything that is been removed from this cube, at the time that it's removed from the cube, we want to argue that it's dv, it's the value that we've assigned it, is the shortest path length. When we start the algorithm, everything is in the cube, so S is empty. And so this is true. Right? When we start the algorithm right here, notice that Q contains all nodes. So every node is in the queue, so S is empty. And so every node in S has the best answer. That's the property that we're going to claim. And then after every loop of this algorithm, every iteration, we're going to say that this property 1, it still holds. Okay? So with your neighbors, let's start reading this proof. I'm going to walk around and try to explain the parts that don't make sense. Okay? Trying to look at all these and come into these steps right here. So start by reading the first two paragraphs.
short V is 19. It's 2. Delta is the shortest. It's not necessarily the direct loop. It's the length of it. Decrease so you can just make that function Q equal to dv. It's updating the row v with the new key dv. dv is something that's So I realize that I've run out of time, unfortunately. I would like you to take this page and bring it back to class on Tuesday. If you have time, look over it, try to understand this piece by yourself. The proofs that we're going to consider are getting more and more subtle. It's harder to just go over them and things like that. I'll see you on Tuesday. Have a good day.